All right, today we are going to talk about double angle formulas. All right, so just like our sum and difference formulas, if you have room on your trig identity sheet, that would be an excellent place for these to go. All right, now I'm going to be actually deriving these, all right, from the sum formulas. So you're not going to have to copy down necessarily everything that I do, all right, just the things that I box are the actual formulas that we are going to care about. Okay, so first we're going to talk about sine. All right, and a double angle formula means that we're looking for sine of 2 times some angle u, right? Of course, double just means you double something multiplied by 2. All right, so that's what we're looking for here. All right, now if we think about it in terms of the sum formulas that we talked about on Friday, all right, we could actually rewrite this as the sine of u plus u, right? Remember Friday we did sine of u plus v. All right, so if we go ahead and plug u in for u and u in for v into our sum formula here, we would get sine u cosine u plus cosine u sine u. All right, well, of course, multiplication is commutative, which means order does not matter, right? So sine u cosine u is the same thing as cosine u sine u, right? So we could actually just rewrite this as 2 sine u cosine u. All right, so this is our double angle formula for sine. All right, so that's one thing that you would want on your formula sheet, on your trig identity sheet. All right, next we'll go ahead and move on to cosine. So if we have cosine of 2u, all right, similarly, we could rewrite that as cosine of u plus u. All right, so if we plug that into our sum formula for cosine, we would get cosine u minus sine u sine u. All right, well, of course, cosine u times cosine u is simply cosine squared u. Sine u times sine u is simply sine squared u. All right, so cosine of 2u is equal to cosine squared u minus sine squared u. All right, so there is a double angle formula for cosine. All right, now, as we can see here, we see a cosine squared and a sine squared. Right, that should bring up some memories from our trigonometric identities, specifically our Pythagorean identity, that says sine squared theta, or u, plus cosine squared u is equal to 1. All right, well, basically, we could substitute out either one of these that we wanted, right? If we wanted to solve for sine squared u so that we could substitute that, right? We would just subtract cosine squared u from both sides, and we'd get sine squared u is equal to 1 minus cosine squared u. And we had to manipulate these before when we were doing trig verifications or simplifying trig identities, right? So this shouldn't be too unfamiliar to you. Additionally, if we were, again, starting with this top one, and we wanted to solve it for cosine squared u, then we would simply subtract sine squared u from both sides. And that would give us cosine squared u is equal to 1 minus sine squared u. All right, so basically we're going to be able to rewrite this formula a couple of different ways, right? Whether we substitute in for sine squared u or for cosine squared u. So let's go ahead and take a look at that. All right, so if we have cosine of 2u equals cosine squared u minus, Well, instead of sine squared u, I'm going to go ahead and replace that with 1 minus cosine squared u. And of course, we would have to distribute this negative to both pieces here. So this would end up being a -1, and this would end up being a plus cosine squared u. So if we combine like terms there, and we get cosine squared u plus cosine squared u, that would be 2 cosine squared u, and then we would have our -1. All right, so here is an alternate form of the double angle formula for cosine. All right, like I said, we could also substitute in for the cosine. So instead of cosine squared u, I'm allowed to replace it with 1 minus sine squared u. All right, so if I have cosine of 2u, and I have, instead of cosine squared u, I'm going to put 1 minus sine squared u, and then we still have our minus sine squared u. All right, again, we go ahead and combine like terms, just negative sine squared u minus sine squared u. All right, so we're going to get 1 minus 2 sine squared u. So here's our third and final form of the double angle formula for cosine. All right, next we'll go ahead and move on to to tangent. So if I want tangent of 2u, all right, again, I can rewrite that as tangent of u plus u. All right, so if I use my sum formula from last week, we could rewrite this as tan u plus tan u all over 1 minus tan u times tan u. All right, so of course, if we do that, all right, well, tan u plus tan u is simply 2 tan u. All right, and tan u times tan u is tan squared u. All right, so here is my double angle formula for tangent. All right, so there's all 5 of our double angle formulas. 1 for sine, all right, 3 different ones for cosine, and 1 for tangent. All right, now typically it doesn't matter which one of these you use for cosine. All right, now, notice that this one has only sine u, sine squared u, but still, if we have sine u, that's good enough. This one deals with only cosine u. This one deals with both. So if you have both sine u and cosine u available to you, you can use any one of these 3. Right? But if you only have cosine u available to you, you would definitely want to use this one. And if you only had sine u available to you, then you would definitely want to use this one. Right? But in general, oftentimes you have both of those pieces, so it won't really matter which one you choose. So how can we use these things? All right, let's say that we are given, all right, that tangent of theta is equal to 4/3. All right, and maybe it wants us to find the exact value of each of the following. Right, maybe it wants us to find sine of 2 theta. Maybe it wants us to find cosine of 2 theta. All right, maybe it wants us to find secant of 2 theta, cosecant of 2 theta, and we'll go cotangent of 2 theta. All right, so we want to find all of these things. All right, well, especially with our sine of 2 theta formula here, we're going to need both sine of theta and cosine of theta. All right, for the cosine of 2 theta formula, we need one or both of sine theta and cosine theta. All right, so we'll start with those first. We haven't looked at these yet. We'll get to those in a moment. All right, so I need to have all of my pieces, sine, cosine, and tangent of just regular theta. Okay, well, we have the tangent. All right, so let's go ahead and draw a triangle. All right, now tangent is positive in both the first and third quadrants. We don't know which one we're in here, but who cares? All right, let's just go ahead and pick one, and the first one is the easiest. So I'll make my angle U over here. All right, tangent, of course, is opposite over adjacent. So opposite here, adjacent here. All right, we can use a squared plus b squared equals c squared, right, to find our missing piece, our hypotenuse here. Or if you just know your Pythagorean triples, this is a 3, 4, 5 right triangle. Okay, well, now that we have our triangle, right, we can easily find sine of theta, which of course is opposite over hypotenuse, and cosine of theta, right, which of course is adjacent over hypotenuse. All right, so now let's do our sine of 2 theta. All right, and our formula for that was 2 sine theta times cosine theta. All right, well, all we have to do is plug all of this stuff in. So we get 2 times my sine of theta is 4/5. My cosine of theta is 3/5. All right, so if I multiply these all together, 4 times 3 is 12 over 25. All right, and then 2 times 12 25ths would be 24 25ths. So we're done with that one. All right, now cosine of 2 theta, like we talked about earlier, has multiple different formulas. Again, it doesn't matter which one you use because we have both sine and cosine. I'll just go ahead and use 2 cosine squared theta minus 1. All right, so I've got 2. Cosine theta is 3/5, but we said cosine squared, so we need to square that thing. And when I do square this, I'm going to get 9 over 25. So I'm going to make 1 25 over 25, right, just for, make it easier to combine like fractions later. So like I said, 3/5 squared is 9 over 25. Multiply that by 2. That's 18 over 25. 18 over 25 minus 25 over 25 is negative 7 over 25. So we're done with that. All right, now we don't have any formulas for secant of 2 theta. That's fine. We know that secant of theta is 1 over cosine of theta. Well, then secant of 2 theta is 1 over cosine of 2 theta. So all we have to do is take our reciprocal here of our cosine of 2 theta. So this is easy enough, negative 25 over 7. Similarly here with cosecant of 2 theta, all we have to do is take our reciprocal of sine of 2 theta. So this would just be 25 over 24. Right? Cotan of 2 theta would be the reciprocal of tangent of 2 theta, but we haven't found that yet. So in order to answer this, we're actually going to have to. All right, so let's try to find tangent of 2 theta. All right, and we know that that is 2 tan theta over 1 minus tan squared theta. All right, well, my tangent of theta is 4/3 up here. So this is 2 times 4/3. All right, all over 1 minus, and tangent of theta is 4/3, and then we go ahead and square that. All right. Now, guys, typically with all of these, really, this would be on the calculator section of your test. So you would just be able to plug that in the calculator and hit enter. All right, but for the sake of demonstration, I'm going to go ahead and work this out. So 2 times 4/3 is 8/3. All right, 4/3 squared is 16 over 9. So this could be 9 over 9 minus 16 over 9. All right, so here I will get 8/3 over, and this would be negative 7/9. All right, so I can keep my 8/3, change my division to a multiplication and flip my denominator to get 9 over negative 7. All right, I can go ahead and simplify here if I want. Right, 9 over 3 simply reduces to 3 over 1. So this will end up being 24 over negative 7. So if tangent of 2 theta is 24 over negative 7, then cotangent of 2 theta is simply the reciprocal of that, which is negative 7 over 24. And we have now found all of the double angle formula or double angles that they asked us to, so we're good to go. Right, there's a couple of other ways that we can use these. Just like on Friday when we started doing these sum and difference formulas, we started them, we used them, and then we said, okay, we can kind of go backwards as well. We can do that with these also. All right, so let's say, for instance, we have 10 times sine x cosine x. All right, well, notice that this looks similar to 2 sine x cosine x, all right, which we know is equal to the sine of 2x. All right, so if I just go ahead and break apart this 5 and change it to, break apart this 10 and change it to 5 times 2, well, then I still have my sine x cosine x. Well, now I have this 2 sine x cosine x, which is just sine of 2x. Right? When these two things are equal, they're replaceable. So I'm allowed to replace 2 sine x cosine x with sine of 2x. So this would simply equal 5 times the sine of 2x. And we're done. All right, similarly, you could look at 1 minus 2. Well, never mind. We'll look at, let's go 8 minus 16 sine squared x. All right, well, hopefully we noticed that this looks like 1 minus 2 sine squared x, all right, which we know is one of our double angles for cosine. All right, so if I go ahead and factor out an 8 here, I'm left with 1 minus 2 sine squared x. Well, I know that 1 minus 2 sine squared x is simply equal to cosine of 2x. So I can replace this with cosine of 2x. So I simply get 8 cosine of 2x. And we're done. All right, so that's kind of the equivalent of going backwards, like we did with sum and difference yesterday. Or sorry, Friday rather. All right, now let's go ahead and look at using this within the context of solving trigonometric equations. All right, so last week we did a lot with solving trigonometric equations. We did it with factoring. We did it just very basic ones where we could just use the unit circle. And then we also used inverse trig functions as well. All right, well, we can apply that to these as well. So let's say we are asked to solve on the interval 0 to 2 pi cosine of 2x plus cosine of x is equal to 0. Okay, well, because these cosines have different arguments, we can't combine them, we can't factor them, again, because these things are different. All right, so we're going to have to do something else. All right, well, we know that we have 3 different formulas for the cosine of 2x. All right, now we are going to have to choose carefully here. All right, one of them has both sine squared x and cosine squared x. One of them has just cosine squared x, and the other one has just sine squared x. Well, because this piece over here is cosine, I want the one that only has cosine squared x. All right, so I'm going to go ahead and use, all right, that 2 cosine squared x minus 1 is equal to cosine of 2x. All right, so where I see this cosine of 2x, I'm allowed to replace it with this. So I can now just say, okay, well, 2 cosine squared x minus 1, and then I still have my plus cosine x, and that's equal to 0. All right, well, I'm going to rewrite this to get it in kind of standard form, right? We think of standard form where we have our squared term first, and then our first degree term, and then our constant number at the end. All right, so I'll rewrite this to 2 cosine squared x plus cosine x minus 1 equals 0. Okay, well now this looks exactly like problems that we did last week. All right, we're going to want to go ahead and factor this first. This looks like a quadratic. Right, if you wanted to replace it with your u's, of course you could. It would look like 2u squared plus u minus 1 equals 0. Because my leading coefficient is something other than 1, I'm going to go ahead and use my trash can method. Now, because it's very simple, many of you may be able to do this in your head. That's fine. But just for demonstration purposes, I'll go ahead and do it. So a times c is negative 2. My b is 1. So I need to find two numbers whose product is negative 2 and whose sum is 1. All right, that's going to be positive 2 and negative 1. All right, well, now I want to keep my leading coefficient, right? So I have 2u plus 2 and 2u minus 1, all right, just filling these in here. All right, well, this is the trash can step, taking out the trash. So I can pull a 2 out here. I'm left with u plus 1, throw that away. I can't pull anything out here, so it stays. And that is my factorization. And of course, I'm not talking about u's, I'm talking about cosine x's. So this is really cosine x plus 1 and 2 cosine x minus 1. Right, of course, whenever we have two factors set equal to 0, we take each one, set it equal to 0, and solve. When I do that with my first factor, I'll get cosine of x is equal to negative 1. And when I do this with my second factor, I will get cosine of x is equal to 1/2. Right, now these are both nice numbers on my unit circle. So I would just look at my unit circle and say, when is cosine of x, or just when is cosine, negative 1? And that happens at pi. So here, x would equal pi. And then we say, okay, where does cosine equal 1/2? And that occurs at pi over 3 and 5 pi over 3. So those would be my three solutions. And we're done. Okay, that's basically all I wanted to go over for today.